And then now comes into the interesting parts, the parts that we stopped at last time. This simplistic view of a set of tasks that are independent, if you look into all the three examples we had here, we never mentioned that tau1 and tau2 depend on each other. We assume that they are independent entities. Each one starts executing, finishing, being interrupted, regardless of the other one, right? So they don't wait for something from each other. In reality, that's not the case, right? Think of a car, for example. I might have given you this example last time. There is a sensor in the wheel that's called the wheel sensor that collects some data, mainly about your acceleration and speed and direction, and then sends this data into your motor control, cruise control, into your logging system, if you have a GPS, into the GPS, into multiple tasks with even multiple criticalities. That means tasks, in fact, share data, right? Communicate to each other. Well, but if you start sharing resources, which includes data or a critical section or some hardware resource like a sensor or input-output device, well, you cannot say I'm independent from each other. If one task is accessing that resource now, you cannot really access, right? So in that case, there is some dependency. The reason that we ignored the dependency earlier is, well, it complicates the analysis. You have to take care of these shared resources. And we said it will create the problem of priority inversion, which means, think of this example. I have a lower priority task and I have a higher priority task. And well, it's a preemptive scheduling, which means if the high priority comes, it has to really kill the lower priority and start executing. The problem might be if the lower priority task is currently accessing a resource that is also needed by the high priority one, you must wait until this task releases it, right? Because it's a resource that has been acquired. Think of a semaphore, for example, or a token. You acquire the token. If you are preempted before you release the token, all the tasks that need that resource will have to wait until you release it, because this is how critical sections work, or semaphores work, right? So in that case, which you have seen in lab 2, and I would assume in an operating system course. So in that case, there is some dependency. I cannot really preempt the lower priority task immediately. And now the behavior of the higher priority task depends on the lower priority task. This dependency creates what we call priority inversion. Why? Why it's priority inversion? Because a higher priority task right now cannot simply exercise its higher priority by preempting anyone, but instead is waiting and depending on the lower priority task to finish its access before it can start, right? So to see an example, let's say we have 3 tasks, okay, tau1, tau2, tau3, and assume that the priority is in the descending order, which means tau1 is the highest priority, tau2 is medium, and tau3 is the highest. And then let's say there is a critical section, which is a resource. It can be a software code, it can be a sensor, it can be hardware, it can be memory, it can be anything. We're abstracting it at the scheduling level. So this, our resource is the green one. And then let's say the higher priority, well, I start here, tau1 is not activated yet. So in my system, well, what task do I have ready right now is tau3. Even if it's the lowest priority, the higher priority ones don't have something to do, so I can schedule it. So at time 0, I can schedule the lower priority task. And then while scheduling, it acquires that resource. Well, it sends the request, it obtains it, right? Or in a software section, it asks for the log and it obtains it. So tau3 accesses the green resource. But then after it accesses, after one time unit, I have an activation from the higher priority task, tau1, good? According to some sort of fixed priority scheduling, let's say RM, for example, I'm going to preempt tau3. I'll start tau1, right? So what happens at this time unit is you preempted tau3 and started tau1. Good. Why? Because you apply rate botonic, for example. And then you start executing tau1. Now, tau1 executes for 2 time units, and then it asks for resource A, for the green resource. Well, there is a problem. You cannot obtain the green resource, right? Think of if you are running 2 threads, the log has been acquired already by a preempted thread. So if tau1 checks for the log, it will find it 1, so you cannot obtain it, right? So in that case, it has to wait. So tau1 is waiting here. Well, the scheduler looks into the system. What do I have to schedule? Tau1 is preempted. Tau2 didn't arrive yet. Then I start tau3. So you start tau3 again, then tau3 continue executing on the resource. Well, tau3 is lucky in that case. But then after executing in one time unit, another task or another job from another task arrives, which is tau 2. Well, as an RM scheduler, again, you look into all the pending jobs. You have one from tau 2. You have a running one from tau 3. Which one to pick? It's tau 2 because it's higher priority. So tau 2 here preempts tau 3 and starts executing. And then it keeps executing for some time. The problem now is during that execution of tau 2 is preempting and delaying tau 3, right? Well, sensible because tau 2 is higher priority. The problem is because tau 2 is delaying tau 3 and tau 1 is waiting for tau 3 to release the lock, indirectly tau 2 is delaying tau 1, right? According to rate monotonic, that's impossible to happen because tau 2 is lower priority. And that's why it's called priority inversion. So at that point, a lower priority task can delay a higher priority task because of access to shared resources. That's why we call it priority inversion. Is there any questions? Stop for a second and take questions. Those examples, if you try to study them in your own without really going through the explanation or we think about it together, it would be very tough, right? So feel free, you guys are here in the lecture anyway, so feel free to ask questions if you didn't get it. Does this make sense to you? Okay, so tau 2 will keep blocking tau 1 until it finishes execution. And then once tau 2 finishes execution, even tau 1 cannot start immediately because again, it's blocked on the shared resource. So what is going to happen is tau 3 will start first, release the lock. And once tau 3 releases the lock, it will be preempted by tau 1. And then tau 1 can continue executing. Make sense? Think of what if the deadline of tau 1 is here. This down arrow we have here, that's not very clear. Tau 1 missed its deadline. Why? Because of the shared resource, right? Because of a lower priority task delayed it, right? And there is a proof that in fact this, or you can think about it intuitively, that this priority inversion can in fact give you unbounded latency. I can always come up with a case where there is an access to shared resource and I have been delayed, right? And in that case, well, you wait indefinitely, right? Is this a problem? Well, it's definitely a very big problem. And I might have mentioned already to you this Mars Pathfinder crashing. I guess I might, maybe in earlier lecture 0, I had a video or a piece of news. Why this Mars Pathfinder crashed? Well, because it had a priority inversion problem in its schedule, right? So this exact problem we are discussing right now caused a multi-billion project to collapse at one point because of it, right? Because of priority inversion. And you guys can watch videos explaining this on YouTube or look into the news. The good thing is that it didn't completely crash because they were able to remotely batch the operating system. So they updated the OS scheduler to, in fact, avoid priority inversion. You might think right now, well, but that's something that is very easy to catch. In reality, not. If you have thousands of lines of code of a kernel and you have a lot of cases, you might end up with facing a priority inversion as simple as this one because you didn't take care of it, right? And this is why, if you remember in lecture 0, verification takes 40% or more of the cycle of the system design. Good. Okay, what is the solution for it? There must be a solution, right? We cannot really say, well, because of sharing resources, I cannot schedule those tasks. Sharing resources is the reality in most embedded systems, not just the Pathfinder, but automotive, avionics, any other one. So what do? There is what we call priority inheritance protocol, PIP. What does it do? So it's a solution that works for fixed priority scheduling, and it's very intuitive. Say, in fact, while a task can block a higher priority task, I must inherit its priority. So what does this mean? Well, if I go back here, tau 2, well, simply blocked tau 1 because it blocked tau 3. But if you say at one point, which is this point here, tau 1, what it's waiting for? It's waiting for a resource from tau 3. So what is the only solution? The only solution is tau 1 is important. Let's make tau 3 important, right? Why we want to make it important? Because there is a dependency chain between tau 3 and tau 1. So the priority inheritance protocol, from the name inheritance, a lower priority task inherits the priority of a higher one to be able to, well, complete its job, release the resource, and give it to the higher priority task. Because right now, well, there is a dependency between the higher priority and lower priority. You must make the lower priority a higher priority one, up until to the point that you break this dependency. Where is that point? When do I break dependency? Once tau3 gives up the resource. Once you give up the resource, you go back again to a lower priority task that no one cares about you in the system, right? So as far as you have something that someone important in the system cares about, you are important. Once you give it up, well, you lost your privilege, right? This is just ironically what the IP is, right? So if we see how does it really work in reality, I will have exactly the same example. I start from time 0, tau3 starts. After 2 time units, it acquires the green resource, start executing on it, and then it's being preempted by tau1. Tau1 executes for 2 time units and wait for the resource. At that point of time, tau3 will inherit the priority of tau1 because there is a dependency that has been created, right? This asking for the resource is creating that dependency. So tau3 start executing. What is different from the previous example is that at this time unit, tau2 is no longer able to preempt tau3. Why? Because according to rate monotonic, you only preempt a task with a lower priority than you. But I have elevated the priority of tau3 to be similar to tau1, which means tau3 right now, at this time instance, at this time stamp, is higher priority than tau2. So tau2 cannot preempt tau3 at this point, which means it allows tau3 to continue executing until it releases the resource. Once it releases the resource, it goes back again to a lower priority task. But at that moment, tau1 is being, well, freed because it has the resources asking for. So it becomes active again. And once it becomes active again, well, it's the highest priority task in the system. So it starts executing until it finishes, and then tau2 can start. So we don't see the priority inversion that we have seen in the previous slide. Again, let's stop for a second and see if that makes sense or you guys have questions. This makes sense? Okay. So one problem here with the system is, well, tau2 is in fact suffering because of tau3 delay, right? Because I elevated the priority of tau3, right? Well, this is necessary to release tau1, but this impacts the execution time of tau2, right? The problem, if we also want to, well, generalize the concept, the problem increases more if you have more than one resource, right? So we had this example here for a single resource, a single critical section, a single sensor, a single I/O that is shared with the tasks. In reality, multiple tasks share multiple resources, right? You don't share one resource at a time. Well, in your thread code, you have multiple critical sections, or in the code you guys have written in lab 1 and lab 2, well, you have multiple tasks that access in the same time, well, the terminal or the SPI or the I2C, whatever interfaces you are using. So those are resources that you also share memory if you have a more advanced system. So in that case, resources are generally several in the system. And this creates the problem of nested resource. So let's see this interesting example. So I have 4 tasks in my system, tau1 to tau4, similar to before. We define the priority in ascending order, which means tau1 is the highest, tau4 is the least. At time 0, let's say the system does not have anything other than tau4 job, so it starts it. Once tau4 starts executing, say for 1 computation unit, it asks for resource A. Does anyone have resource A, the green resource? No, so I can acquire it easily. So I obtain the lock and acquire it. And then after I execute for 1 time unit, I'm being preempted by a higher priority task. Let's say we assume rate monotonic here. So tau3 arrives, and then it preempts tau4. Tau3 starts executing. Well, similar to the previous case, transfer 1 time unit, asks for another resource now, which is resource P, the orange resource. Is resource P free? Yes, no one has it, so I can acquire it. Start executing for 1 time unit, and then tau2 arrives. Tau2 is a higher priority, so I'm being preempted. Put in mind that at this time unit here, time unit 4, the 2 resources are busy, right? They are being acquired, but not released yet, right? This is important. And then tau2 starts executing. It goes through 3 computation units, and then afterwards, it's being preempted by the higher priority tau1. Tau1 starts for 1 computation unit, and then it asks for resource P. Well, what happens for resource P? It's not free, it's busy, right? But now we have learned about priority inversion protocol, priority inheritance protocol, and then I can solve it. How do I solve it? Once tau1 asks for that resource, who has it? Tau3, elevate the priority of tau3, right? So I do priority inheritance here, which means at this time unit, tau3 obtains the priority of tau1, right? By doing this, you enable tau3 to run because now it has the highest priority in the system. It runs for 1 time unit and releases the resource. Once it releases the resource, well, what happens? Oh no, I didn't release the resource yet, so my apology. It executes in resource P, but then asks for resource A. Here comes the nesting of the resources. Now it becomes a little bit more problematic. Tau3 is asking for resource A. Who has resource A? Well, resource A is owned by tau4. If I apply exactly the same algorithm, priority inheritance, I would say tau4 would have to get to the priority of which task? What do you think? Tau1 eventually, yeah. So it will take tau3, and then tau3 is, well, now tau1, so it will get tau1 priority, which means, well, tau4 will get the priority of tau1 and start executing. Once it gives up the resource, the green resource with resource B, which is being asked by tau3, it will go back to its priority, right? Because we said you only inherit the priority until you release the resource that, well, the important task is asking about, right? So at that point, you go back to your original priority, which means you get blocked because according to rate monotonic, there is a higher priority task that is waiting for that resource, please. Yeah. Well, we use W and SW for waiting for the resource. So it's basically, think of it like from a semaphore perspective or a critical section perspective, you acquire and then you release. So W, wait for the resource until you obtain it, and S means basically you are done with that resource, right? So you release it. So once I'm done with the green resource here, I release it, which means I go back to my original priority. And then tau3 will start executing on the A resource. Once it finishes it, it releases it, but no one is asking for A for now, so it doesn't really matter, nothing is changing. But then once it releases A, it goes back to B, which it has. So it will continue executing in B. And once it releases B here, tau1 can start executing. So at that moment, tau3 will lose its tau1 priority and go back to its original priority. And then you start executing tau1 that has been waiting up until this moment for that resource. So tau1 start executing on that resource, it acquire it, finish it, and then go back to its computation and finishes here. Once it finishes, well, tau1 is the highest priority, I'm done. The rate monotonic scheduler will look into the task queue and pick the one with the highest priority. What is the one with the highest priority? Is tau2. Start executing it until done, and then go back to the one with the next priority, and then etc. Does this make sense? You see how nested resources can, well, you can apply the BIB algorithm basically iteratively, right? Okay. The problem with this is you might be suffering what we call double blocking. So if I go to that example here of tau1, let's say tau1 is going to be asking for 2 resources that are owned by 2 different lower priority tasks. So here, well, again, like the similar setup that we do at the beginning, the lower priority task starts, acquires a resource, and then get preempted. And then the next one starts, acquires another resource and get preempted. So at that moment, again, A and B are completely busy. They are acquired and not released. The higher priority task, which is tau1, start executing and then ask for B. So at that moment, you have to wait to, well, release B. So you inherit the priority, tau2 inherit the priority of tau1 because B is owned by tau2. Once tau2 finishes, tau1 can start. And then it continues for some time. And then it asks for another resource A. And then again, well, A is owned by which task? By tau3. So you have to wait for it. You inherit the priority. You allow tau3 to go through. And then once it finishes executing, you go back again to tau1. So we have applied the priority inheritance protocol, and we don't have any priority inversion, right? So the problem we have discussed at the beginning of this section is solved, right? But now we are focusing on another problem, or a little bit on optimization. If I think about tau1, which is the highest priority task in the system, you see that in this example, it's suffering from what we call double blocking, right? What is double blocking? The two resources you are asking for, you have been waiting for. So you have to wait for 2 periods of time here, blocked by a lower priority task. Okay. Well, can I generalize this? Yes. If you have n tasks in your system, well, I can really be delayed by n-1 blockings, right? Because every single lower priority task might be acquiring a resource that I want, and I have to wait for it, right? Well, why we care about this? Because put in mind, tau1 is the highest priority task in your system. Well, in the Pathfinder example, that the one we gave, for example, it might be this is the, well, controlling engine, right? Or this is the environment sensing to make sure that you don't fall yourself into something unsafe. Or this is the airbag in a car, right? Or this is the motor control in a car, right? Or this is the base regulator in a pacemaker in a patient. So this is the one that you really care about. Being blocked by every single lower priority task, this defeats the fixed priority scheduling algorithm, right? Because RM originally, main purpose of fixed priority is to say the task with the highest priority does not care about the lower priority ones, right? Every time I arrive, I preempt the lower priority one and I continue executing. Even with BIB, right now, that's not really the case. Every time I ask for a resource that is being shared by a lower priority task, I have to wait for some time. If I ask you, and this is in fact a topic of research papers, if I ask you a question in the exam as well, let's compute the worst case execution time of tau1, and I give you some example of shared resources. So what do you think? How can we do it? So in other words, if we put it into numbers, I will tell you, let's say, well, we take the example of 2 resources first. So let's say resource A is a critical section, which is like number of instructions, which means I can really bound its execution time. For example, if this 100 instructions, I know that it's an add or subtract or something else. I know how much time does it take in the pipeline to execute it. So I can derive a computation bound on the number. So let's say resource A, in worst case, anyone that is accessing resource A, if it's uninterrupted at all, it takes 30 cycles to finish. And then resource B might be 50 cycles. And then I tell you, well, tau1 can really ask for each resource once, for example. So you have to bound how many times you ask for the resource, right? So in that case, to bound the overall execution time of tau1, in addition to its computation, you have to add all the blocking times, right? If you look into the figure we have here, I started here and I finished here. If I try to assess this period of time, it's composed of these blue parts, which are my pure computation, but it's also composed of, well, the colors, which is my execution on the resource. And the third part is my blockings, right? The parts that have been waiting for the resources to be released, right? Can I bound the computation? Yes, this comes from the task bound. We have CI, remember, from the task model, sorry. So we know that tau1 has C1 and T1 and D1, for example, right? C1 is my worst case execution time. So I have a bound on C1. In our example here, C1 is what? 2 units, 2 units, 1, so it's 5 time units. So I have a bound on the blue part. What about the green and the orange? Do I have a bound on them? These examples are a bit involved with mathematics, so you guys have contributed to make sure you follow. Or you want me to repeat, I can repeat. So simply we said, I look into how to analyze a task. What a real-time engineer, really real-time systems designer do in analyzing a task. It looks into all the possible delays or latencies that are suffered by that task, right? In our example here, these are 3 things, or in reality 4 things, but I'm combining the orange and the green. The first one is my original computation. This is the one that we have been considering last lecture without talking about resources at all. And we said, do we have a bound on the blue one? Yes, this comes from the task model, right? Which we said before you can obtain using static analysis or running the tasks for millions of times and then take the worst time, right? So I have C1 number as part of it's given to me, right? And in this example, it's 5 time units. And then I look into the second type, which is the orange and the green, which is accessing the resources. Do I have a bound on them? Can I really give a similar number to 5? What do you think? Yeah. Yeah, I already give you the numbers of accessing the resources. I told you that for all the tasks, that's the worst time you take to access these critical sections, which means if tau1 accessing the orange resource, which is B, in worst case, it can take 50 cycles, right? So in that case, for the orange one, I take 50. And well, as your friend said, for the green one, I take 30, right? Well, this is a very large number here in our example. Yeah, let's keep them and ignore about the time unit stuff, but have the numbers. So it's 53. Then the harder question comes into play. There is one remaining component. If you sum all these up, this in fact does not resemble the total worst case execution time, right? There is one additional component that we left behind, which is the time that you have to spend being blocked waiting for these resources. How can I bound these? What do you think? Which is basically the empty ones here, those ones, the blocking one here and the blocking one here. What do you think? Yeah. Yeah, exactly. So it's basically saying, okay, what I'm doing right now, I'm waiting for a lower priority task to release it. What is the worst instance? The worst instance that I ask for the resource just directly after, one cycle after the lower priority one obtained it, right? Which means I have to wait for the full period -1, but you can ignore the -1 now, the full period of this critical section to be executed by the lower priority task. So for example, here, if I'm waiting for the B resource, the orange one, and I can ask, well, in our example, well, here, tau2 finished most of its time in B2, but in reality, in worst case, that's not the case. In worst case, tau2 are just barely started, right? So in that case, I have to spend the 50. And then what about the A1? Similar. I can assume in worst case that I ask for A just directly after tau3 obtains it, which means I have to wait for tau3 to release it, and this is going to be 30 time units, right? So this would be the total worst case execution time of my task, right? And then as part of the task model, if I have a deadline here that is given to you, then you can do your usual scheduling algorithm by saying, well, do I have this task schedulable, which means it meets its deadline or not? You compare the total execution time to the deadline. If it's less, then yes, it's schedulable. If not, then it's not schedulable, right? So this is an exercise that is done to analyze that task, right? Makes sense. It might be an example of a problem in the midterm, right? There's no midterm in the final exam. Yeah.
If there were more tasks, you have to consider the possibility that resource A or B got blocked by another lower priority task.
Excellent question. Excellent question. Up until now, we're talking about the task that is the highest priority, which means once you ask for a resource, you have to wait only for one lower priority task to release it. And this was the next part I was going to talk about. If you want instead to analyze tau2, for example, well, the reason that maybe it's not very suitable to talk about tau2 is we know that tau2 is lower priority than tau1 anyway. So in reality, tau2 can be preempted by tau1 at any time. And also tau2 might be waiting for tau1 asking for resources all the time. So you cannot really drive a realistic bound. But in reality, in real practice cases, that's not the case. Why? Because people, maybe that's an engineering question, it's a little bit tough question, so it's a bonus mark. So what I'm saying right now might make sense theoretical. That we were able to drive a bound, and you have to pay attention. We were able to drive a bound on the highest priority task because this is a fixed priority schedule. Tau1 is the highest one. It preempts anyone else, so it has no problem at all. And the only problem is that it has to wait for one resource to finish from one lower priority. On the other hand, if I was to analyze tau2 or tau3 instead, it's a little bit more complex because assume, for example, I'm analyzing tau2 and the resource is owned by tau1. Now there is no priority in inversion or anything. Maybe tau1 finishes the resource and starts exactly the same resource one cycle after, right? So in that case, you obtain it, right? So there is no ordering, it's fixed priority, which means theoretically, you have an infinite bound, like there is no bound, right? I can wait indefinitely. But in reality, that's not the case. So the bonus mark is why you might think that's not the case. What conditions I can add, which are practical conditions, that can give me a bound even in the medium or lower priority tasks? What do you think? From the shared critical section perspective, please. Yeah. Well, that's an excellent answer, but now you're changing the scheduling algorithm, right? So for example, you are saying, well, I apply something like EDF, where, well, the more time I'm waiting, my deadline is approaching, so I get my priority elevated. But I would say it's an excellent answer. It might be a practical answer, but it's the easier answer here. So let me constrain you more and say, I leave RM as is. It's fixed priority. I don't change my priority, right? But you get the bonus mark because it's a correct answer. Yeah, please. Yeah. Yes, that's a very important one, but yeah, but that's partially true. That's its own, it's a necessary but not sufficient, which means I need to do this, but it's not sufficient. Is it only the time when I access the resource? How much time? Because I already gave you that bound, right? There is already a bound on once you access a resource, how much time you spend on it, right? But there is one additional element. So if you remember the interrupts, we have went through it. Yeah. Exactly. Thank you. So these two combined are sufficient to drive a bound. How much time do I spend in the resource? And how many times a task in worst case can access that resource? If you remember our analysis for the interrupt, we have done exactly the same thing. We said you have your interrupt frequency and you have your interrupt busy time. And then you multiply both together, you get the utilization of the interrupt, right? So now if I can say in worst case, tau one during one period can only access a resource 3 times. In worst case, tau 2 would have to wait for all the 3 times from tau 1. Each time is going to consume 30 cycles. Then in total, I get 90 cycles, right? And the same thing for resource 2. So you have to bound number of times accessing a resource and how much time you spend there. Luckily, this is in fact a practical assumption because this resource is, for example, a sensor. You know from your software that I need to access this sensor, well, 1 time every 1 millisecond, 10 times. There is an inherent design that really limits how many times you access that resource, right? So it's not theoretical. Well, even if theoretically it's infinite, in reality there is some sort of a bound there, right? So yeah, everyone gave an answer. You guys send me your email, your name by email after the lecture. Yeah, it's an interesting discussion. For everyone else, is that clear? So if I'm able to bound how many times each task can access each resource, and how much time any task in worst case takes for a resource, I can derive a bound, no matter really whether for the highest priority task or the lower one. Good. But now going back to our discussion, if I want to, well, if I care about the tau 1, which is the one with the highest priority in the system, and ignore about like bounding all the other tasks, we still suffer from this double blocking, right? Yes, we accounted for it, we obtained the bound, but can we do better? I mean, as I mentioned, making the higher priority task wait for every single lower priority task to release a resource in worst case is something that defeats the fixed priority concept because well, at certain points I'm no longer higher priority. I have to wait, right? So what we call the multiple blocking problem. A higher priority task can be blocked multiple times because of accessing resources that are shared by lower priority tasks. BIB algorithm does not solve it, right? How to improve over it? Well, we can improve by adding the limitation that we also discussed right now. But instead of bounding it by the number, I put by design, by construction, a limit on the ability of lower priority tasks to enter a critical section. And here I'm giving you an example of a resource, but let's see it in reality. Sometimes it's called priority seal, which is a very common algorithm in real-time systems. So let's see how does this really work. So I start my same example, tau 3 lower starts, asks for A, and then being interrupted by tau 2. Well, here tau 2 is blocked by tau 3. Why tau 2 is blocked by tau 3? This example is a little bit incorrect. Sealing of both resource, priority of tau 1. Ah, yeah, I see. Okay. So this is to apply to okay, that makes sense. This is to prevent the double blocking. So you look into your system at the beginning and you say, I look into, for example, the highest priority task. I see what resources it accesses, right? It's resource A and resource B. So what I'm going to do is I say, at any point, so I inherit the priority. Well, in an essence, you inherit the priority of the task, but not for the lower priority task. Instead, you inherit it for the resource itself, right? This is in reality what it is. This is why it's called priority seeding, is you look into your resource, you look into all the tasks that access this resource, and you assign a priority for that resource according to the highest priority of a task that is accessing it. For example, just to imagine how we do it. That one is accessing resource A and B, orange and green. In that case, I would say these two resources, in fact, have the priority of A, which means any other task, any task in the system, when accessing A or B, in reality, they will have the highest priority, which is tau 1 priority. So by doing this, tau 3 starts executing in A. Once it starts executing in A, it gets the priority of tau 1, even before tau 1 comes. That's the difference. That's the subtle difference between priority sealing and priority inheritance. Is you don't wait for the higher priority task to come. You just inherit the priority from the resource itself. And then at this moment, tau 3 is no longer interrupted by tau 2. Why? Because tau 3 has the highest priority in the system. So for it's basically at that moment here. And then only after you release the resource, you go back to your original priority. So tau 3 here goes back to tau 3 priority, which allows tau 2 to start. So in that sense, tau 2 is blocked by tau 3. But then you start executing. And once you start executing, well, tau 2 requires resource P. Same thing applies. Resource P has the highest priority of tau 1, which means, in fact, tau 2 cannot be interrupted by tau 1. So you release the resource. Up until this point, it seems that, in fact, counterintuitive, because you delay the tasks even at the beginning, right? But the premise here is once you release all these resources, so in other words, what priority sealing leads you is you might suffer some delays at the beginning, but once you start, you run uninterrupted, right? So once that one starts here, it has all the resources it needs, right? So which means it's only blocked once by the tau 2, right? Compare this to the original problem here where you are being blocked twice, once by tau 2 and once by tau 3. Questions? We have seen so many figures and scenarios. So if you have questions, ask. If you are lost, ask as well.